Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Membrane separation process. In this video course, you will learn what is membrane separation, benefits of membrane separation versus other processes, types of membrane and membrane performance, structure of membranes, classification of membrane processes and applications. I would appreciate if you subscribe to the channel. It will motivate us to produce more valuable knowledge content for your career progress. So subscribe now before you forget. Membrane separation is emerging as an alternative technology to conventional separation technologies. Membrane technologies are becoming increasingly important in the petrochemical industry as an alternative to traditional energy-intensive separation processes such as distillation. It is replacing the conventional water treatment processes in the water demineralization applications. It has gained acceptance in the wastewater treatment and gas treatment processes to meet the stringent land disposal and environmental norms. Thus, the membrane process is used for both gas and solid liquid separation applications. Membrane separation process offers numerous advantages over other mass transfer processes. 1. High selectivity. 2. Low energy consumption and moderate cost to performance ratio. 3. Compact and modular design. Typical applications of membrane process include gas separation, evaporation, demineralization of process water, and seawater desalination. What is membrane separation process? How is it different from other separation processes? What factors are working in its favor and contributing to its acceptance by the industry? Come on, let us move on to find out. Membrane separation technology is a separation process in which a membrane layer is used to accomplish the separation of the desired species in the feed stream. The membrane acts as a specific surface that permits one or more species to move faster than another or other species. The selective transport of molecule through the membrane is achieved either by application of pressure or a concentration gradient on the other side of the membrane. This figure shows the membrane cell in which a membrane layer has been installed. The feed enters at the top and flows through the cell over the membrane surface. Certain species of the feed, depending on the pore size or solubility, pass through the membrane and is collected on the other side of the membrane as permeate. The other species are retained in the feed and leaves the cell as retentate or residue. Membrane types. With the emergence of several newer applications for membrane technology, there has been constant efforts to develop membranes of materials that will deliver high selectivity and permeance. There are two types of membranes. 1. Microporous membranes. 2. Dense or non-porous membranes. In non-porous membranes, the pores, if any, are less than few angstrom in diameter. In microporous membranes, the separation is based on diffusion rate through the pores. In non-porous membranes, the diffusing species must dissolve into the polymeric membrane and then diffuse through the polymer. Hence, the separation is based on difference in solubility and diffusion rate through the membrane. Non-porous membrane and separation mechanism. As explained earlier, in microporous membranes, the separation is by the diffusion only, and the analysis is simple. In the case of non-porous or dense membrane, separation takes place by combined effect of absorption in the polymer and diffusion. Applications such as gas separation employs non-porous membranes. Hence, let me now throw some light on the mechanism of separation by a non-porous membrane because it is emerging as a novel process in gas separation, both on standalone basis but also as a hybrid technology. The transport of molecules through the non-porous membrane takes place through three steps: selective absorption on polymer surface, selective diffusion inside polymer, desorption of the molecules on the opposite side of the membrane. Thus, the separation in a non-porous membrane is based on the selective solution and diffusion. In other words, physical chemical interactions between the membrane material and the permeating molecules, and not the relative volatility as in conventional separation by distillation. What is driving the interest in this technology is opportunity for potential improvement in energy efficiency and environmental benefits. Illustrated in this figure is a mechanism of separation in a non-porous or dense membrane. The component 1 shown in blue color is first absorbed on the polymer surface, then diffuses through the membrane. Finally, gets desorbed from the surface of the membrane on the other side of the membrane. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. Membrane performance. Membrane performance for a given application is the key determining factor while making a choice between membrane technology and other competing technologies. The overall and component balance equation across the membrane module is written as follows. The overall material balance is F is equal to R plus P, where F is the membrane feed rate in moles per second, P is the permeate flow rate in moles per second, R is the retentate flow rate in moles per second. The component balance is written as follows. F times XF equal to R times XR plus P times XP, where XF is the membrane feed concentration, XP is the permeate concentration, XR is the retentate concentration. The performance of the membrane is characterized by two parameters. One, selectivity alpha, 2, permeate flux J. Selectivity and permeate flux are the intrinsic properties of separation membrane. Selectivity and permeate flux are known to be strongly dependent on process conditions. The selectivity alpha is defined as the ratio of the permeability of component I to the permeability of component J, that is Pi divided by Pj. Permeate flux. Membrane productivity is a measure of quantity of a component that permeates through a specific area of membrane surface in a given unit of time. The membrane productivity is characterized by permeate flux J. Permeate flux relates the product rate to the membrane area needed to achieve the separation. The permeate flux J is expressed by the equation J equals Q by AT. Where Q is the mass of permeate in kg, T is the operating time through the membrane in hours, A is the effective membrane area in square meter, J is expressed in kg per meter squared per hour. The permeance or permeability of the membrane material P by L is calculated as Pi by L equal to Ji divided by Pif minus Pip. Where L is the thickness of membrane in meter, Ji is the permeation flux of component I in kg per meter squared per hour, Pif and Pip are the posture pressures in the feed and permeate side of the component I. Shown in the table below are the values of permeance and selectivity for separation of propane and propylene by ZIF8 membrane. The values of permeance or propylene in the units given are 206 and that of propane is 4.6. The separation factor is 45. The propylene-propane gas separation, the propylene has a selectivity of 40 and hence much easier to separate. If an attempt is made to increase the selectivity, the permeability will decrease and vice versa. Thus, there is a trade-off between selectivity and permeability or permeate flux. The key drawbacks of almost all membranes are low permeability and selectivity. If membrane process has to be economically viable alternative to conventional separation technologies such as distillation, there are minimum permeability and selectivity parameters for the membranes. At today's membrane prices, the economics will be favorable if the values of these parameters are 1. Permeability greater than 1 barrel, 1 barrel equal to 3.4 times 10 to the power minus 16 mole per square meter second Pascal. Selectivity greater than 35. Single stage versus multi-stage membrane system. Single stage membrane separation process has limitation in obtaining high permeate. In order to increase the membrane separation factors for maximizing product recovery and purity, A multi-stage membrane separation process is normally used. The figure shows a typical multi-stage membrane system and the flow arrangement. It consists of several cells of membrane connected in series. The feed enters the first stage. After a partial separation of desired molecules, the partly depleted feed moves to the subsequent stages in series until the required separation is achieved. The permeate is collected from each stage and led to the permeate collection tank. The retentate is collected from the last stage. Membrane modules. Membrane modules have been developed in several structural forms to meet the varied applications across industries. Since cost is an important factor, efforts are to increase the packing density, whereby the area per unit volume of the membrane module is increased. Membranes have been developed out of materials that include polymer composite membranes, carbon molecular sieves, zeolite-based membranes. Polymer and composite membranes. Generally, composite membrane consists of a selective layer of non-porous membrane and a porous substrate layer. The thin selective layer provides the overall separation function, whereas the substrate layer provides the mechanical strength. A typical example is a GFT PVA composite membrane that comprises PVA selective layer and a PAN supporting layer and a non-woven support layer. PVA is polyvinyl alcohol, PAN is polyacrylonitrile. This figure illustrates the structure of a composite membrane. Note, the membrane has a top non-porous selective layer supported on microporous and non-woven support layer. A photograph of a sample of composite layer is shown at the top. Apart from the polymeric membranes, inorganic membranes based on silica, alumina or zeolites have gained attention in the recent years due to their superior chemical and thermal and mechanical stability. The inorganic membranes exhibit greater flux and separation factor than polymeric membranes, especially for certain special applications in harsh environments, but they suffer from high cost and low processability. One of the major hindrances is the high capital cost, particularly for high volume applications. The cost of membrane rises linearly with size, whereas the cost for major process equipment decreases with size. Membrane modules with high surface area are required to reduce the capital cost to make it more attractive for investment. New engineering approach uses spiral wound or hollow fiber membranes. Both spiral wound and hollow fiber membranes are packaged in elements called modules. This new design has led to major cost reduction. Shown in this figure is a hollow fiber membrane unit. Both vertical and horizontal placements are used. Illustrated in this figure is the cross section of a hollow fiber membrane module. The membrane is enclosed in the housing. The permeate is collected in the central pipe as shown. Observe the feed the permeate and the retentate streams movement through the hollow fiber unit. Classification of membrane processes. Membrane processes are classified according to the types of membranes and the kind of driving force used for achieving the fluid-solid transport across the membranes. In general, when pressure is used as a driving force, the membranes are classified into four broad categories. They are microfiltration, ultrafiltration, nanofiltration, and reverse osmosis. Other membrane processes that has emerged recently are evaporation and gas separation. Since the pore size determines the selective transport, moving from MF through UF and NF to RO, the hydrodynamic resistances increases. Consequently, higher driving forces are required. Microfiltration. Microfiltration is characterized by membrane having large pore size. It is capable of separating suspended particles in sizes ranging from zero point 0.1 to 0.01 micrometer. Ultrafiltration. Ultrafiltration is characterized by membrane having medium pore size. UF is capable of separating suspended particles in sizes ranging from 1 to 20 nanometers. Both microfiltration and ultrafiltration are pressure-driven membrane processes. The sieving effect or separation is the effect of selective diffusion based on pore size. For ultrafiltration and microfiltration, salt retention is zero, that is, it removes only suspended particles and not dissolved solutes. MF and UF membranes operate at 0.1 to 3 bar and 3 to 10 bar respectively. Nanofiltration. Nanofiltration is characterized by membrane having pore size varying from 0.1 to 1 nanometer. NF is capable of separating lower molecular weight uncharged as well as charged molecules. It holds back the charged species such as polyvalent ions and large monovalent ions while allowing smaller monovalent ions to pass through. Nanofiltration is a pressure-driven membrane process and in terms of separation performance falls between ultrafiltration and reverse osmosis. The sieving effect or separation is combined effect of selective diffusion based on pore size and electrostatic repulsion. The salt retention is considerably lower for nanofiltration membrane than reverse osmosis membrane. The operating pressure is in the range of 20 to 30 bar. Due to high pressure, energy required per meter cube of permeate flow is higher than for MF and UF membranes. The pore size of dissolved salts such as chloride and sulfate in water are 0.12 nanometer and 0.23 nanometer respectively. Hence, if you have a nanofiltration membrane of pore size 1 nanometer, the NF permits these salts to pass through, while larger size ions are retained. Reverse osmosis. Reverse osmosis is the membrane separation process in which a semi-permeable membrane permits solvent to pass through at a faster rate than the dissolved solids or salts. As a result, the solvent-solid separation occurs with solvent being the permeate or pure product. The driving force of the RO process is the applied pressure. The actual operating pressure available for a given RO unit is known as the differential pressure or the net driving pressure. The net driving pressure is the difference between the feed water pressure or applied pressure and the osmotic pressure. What is osmotic pressure? Osmotic pressure is related to the natural process of osmosis. Water flows through a semi-permeable membrane from the side with lower concentration of dissolved solids to the side with higher concentration of dissolved solids. The reverse osmosis process has to overcome the osmotic pressure to operate. The pressure is applied to overcome the osmotic pressure. The membrane permits the selective transport of solvent rather than the solute. The mechanism of RO, as explained earlier, is the combined effect of sorption and diffusion. The solvent gets absorbed on the polymer surface, passes through the membrane, and then gets desorbed on the other side of the membrane. The osmotic pressure POS is determined experimentally. The osmotic pressure depends on the total dissolved solids TDS in the feed water. The higher the TDS, the higher the osmotic pressure required. Typical applications of the different membrane processes are outlined in the tables below. Type of membranation process: microfiltration. Applications: removal of bacteria and suspended particles from water as well as in industrial wastewater treatment. Ultrafiltration. Applications include removal of high molecular weight products from low molecular weight products, used in food processing industry in clarification of fruit juices. Nanofiltration. Applications include water purification by hardness removal, also in peroperation, which is separation of ethanol and water mixture. Reverse osmosis, permeable to only to water and not to solutes, used for production of pure drinking water, also in desalination of seawater. Gas separation. Applications include propylene product recovery in polypropylene plant and ethylene recovery in MEG plant, also in hydrogen separation. Peroperation. It involves a change of phase from liquid to vapor as a liquid passes through the membrane, used in the ethanol water separation. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.